Hello everybody, and welcome also from my side to the IEEE Big Data 2020. My name is Markus Götz and I am from the Karlsruhe Institute of Technology in Germany. Today I'll be talking about HeAT, a distributed and accelerated tensor framework my collaborators and I have been working and researching on. Before we dig deep into the topic, let's talk about big data and our analysis challenges in general. I think I'm preaching to the choir if I'm saying that we're observing that more and more data is collected every day. This is not only the case in industry, but also in science, or specifically the natural sciences where we work in. Our data producers are manifold. Can be sensors, experimental measurements, automated programs that monitor or simulate processes. We usually capture our data in multidimensional numerical arrays that we then analyze using data-driven models. This can range from very simplistic statistical approaches like mean and variance calculations to highly sophisticated artificial intelligence and machine learning models. On the one hand, we are very fortunate that we usually have only a single, homogeneous, well-curated data source. On the other hand, we face several big data challenges. One of them is that we have very monolithic, large-scale datasets, where large is several terabytes up to petabytes of data that cannot be decomposed and needs to be analyzed in one go. At the same time, we require a certain snappiness or velocity of the processing. Before we started developing HeAT, we had a look at the state of the art in numerical big data analytics. We found out a couple of things. First, Python is highly dominant in the field. This is mainly due to its NumPy and SciPy programming libraries. The whole stack is confined to a single CPU-only processing node. What we needed is more, because our hardware landscape is different. Next to traditional CPU processing, we make increasingly use of accelerator technologies like GPUs. Also, we network individual processing nodes to commodity or high-performance clusters in order to fan out and distribute computations as to be able to tackle the large datasets I was mentioning earlier. None of the tools in this landscape provided by Matt Turk on the right side fit our need at that point. Meanwhile, there's some development in the field and a whole potpourri of computational and distributed numerical big data engines have appeared. HeAT is an acronym and stands for the Helmholtz Analytics Toolkit. It is a distributed and accelerated tensor framework and by design is intended to bridge the gap between classical numerical big data analytics and cluster computing. Like the existing tools in the field, it is developed in the Python programming language and intends to offer a NumPy-like programming interface to the user. It goes beyond the classical tools by offering acceleration via CUDA GPUs and distributed processing in cluster environments via the message passing interface, or in short, MPI. On top of that, it also includes a set of high-level algorithms. This starts from simple basic algebraic operations like plus, minus, to sklearn like classical machine learning algorithms like regression, k-means clustering, and so forth, up to neural networks that are PyTorch-like but can be run and trained in a distributed fashion. HeAT itself is a collaborative effort between three research institutions. On the one hand, there's DLR, German Center for Aeronautics and Aerospace, the Jülich Research Center and its Jülich Supercomputing Center, as well as KIT, the Karlsruhe Institute of Technology. The core of HeAT is a data structure that is called DND array, which stands for Distributed N-Dimensional Array. As long as you're on a single computational node, a DND array is equivalent in its behavior to an ND array in NumPy, or a multidimensional vector in the R programming language, for example. However, in a distributed environment like a cluster system, for example, a DND array becomes more than that. It allows you to decompose the data into subparts that are disjoint and is distributed across all the processors or nodes within your cluster system. For this, HeAT allows the definition of something that we call split axis. The split axis defines the single axis along the multidimensional array along which the decomposition is performed. Let's look at an example on the right hand side. In the top left we have the raw data that is not decomposed. On the right hand side and at the bottom we have examples where three processes P0, P1 and P2 are involved. In the top right example we have set the split axis to 0, so the tensor is decomposed along the zeroth dimension. As you can see, P0 gets the first two rows, P1 the second two rows, and P2 the last row of the data. It is equally possible to define other split axes. Setting it to 1 or 2, for example, will result in the data decompositions you can see at the bottom. This way, users can freely choose how their data is being handled while maintaining a high-level interface to the data chunking. We are utilizing the PyTorch programming language to not only hold the node local data portions, but also to serve as an eager computational engine. This allows us to not only use CPU computations, but through PyTorch's sophisticated GPU CUDA backend to also accelerate computations and offload to GPUs. The split semantics in HeAT's D&D array is straightforward. There are two options, setting it to none or something different. Setting it to none will result in a redundant copy on each of the computational nodes in the cluster system. This may seem counterintuitive at first, but can greatly speed up computations by not needing to exchange data over the wire. Equally, decomposing a large dataset makes it possible to store all of it in memory at once and is automatically load balanced by the framework. Whenever you perform an operation that involves the split axis or performs computation like reductions across the split axis, message exchange is automatically performed by HeAT. Let's look at some details on how HeAT actually performs processing and operations. Generally, it follows something that is called the bulk synchronous processing or BSP-inspired programming model. This means it asynchronously performs super steps in which actual computation is happening. Each of the processing nodes can exchange data with all the others in order to obtain partial or complete results. At the same time, there are so-called global synchronization points. These synchronization points are, for example, program start, end, or disk operations. A special synchronization point is something that we call resplit. In such a resplit, a D&D array, triggered by the framework or the user, reassigns the split axis of data. For data transmission, we are using a technology that is called Message Passing Interface, or MPI. Originally, it is from the domain of high-performance computing and allows the utilization of special interconnect hardware like InfiniBand. However, MPI is also able to communicate via shared buffers or simple TCP/IP communication, making it usable not only on notebooks and workstation, but also commodity clusters. Since you know now all the details of HeAT, let's have a look on how we can actually use it to perform big data analytics tasks. I have brought you some examples here. At first, let's have a look on how to create a very simple vector. Below you see some Python code for it. At first we import HeAT as a module. Then we create the vector A with 10 digits from 0 to 9. Printing out the vector will result in the output that you see below. It basically tells you it's in the D&D array with the numbers 0 to 9 of data type int32 allocated on the CPU without any split axis set. Having a vector of data is no good if we can't perform any operations on it. So let's have a look at one more example on how to do that. On the next slide, I'm showing how to do a vectorized operation on it. The code is the exact same like the previous slide. The only thing I have changed is the +3 highlighted in green. What it will do is it will add the number 3 to each of the entries. So it does not only perform vectorization, but also broadcasting of the operands. As you can see here, the result is now the range from 3 to 12. Below, you see an example of the NumPy library that does the exact same. As you can see, the interface or programming API of HeAT is the exact same syntactically. Let's have a look now how I can use GPUs as accelerators for these computations. On the next slide, I have again the same code as before. What I have changed now is that in the vector initialization, I'm passing an additional parameter called device. The value set is set to the string GPU. As you can see, the data is now allocated on a CUDA-capable GPU on my machine. Obviously, this can become quite tedious if I have to do this for every vector that I'm initializing. Therefore, HeAT allows to set a default device for all the computations that are executed from then on. For this, I can use the useDevice function, again with the string GPU as parameter. This capability is now very similar to what a PyTorch or TensorFlow computational library can offer you on a single node. However, HeAT can do more than that. As mentioned before, it can do cluster computations. Now let's have a look how to use the split access and distributed computations in detail. For this, I have brought you an example where I'm loading data from disk and I'm performing an operation on it in a cluster computing setting. The example encompasses two cluster computational nodes named 0 and 1. Using the htload function, I am accessing an HDF5 file called iris on my disk. As you can see also in green, I have specified the split equals 0 parameter. This means my data is decomposed between 0 and 1. Overall, the shape of my data is a 150 by 4 matrix. Due to the split modifier, however, my data is internally actually decomposed. I can ask each of my computational node what's the data portion that they have received. Both would tell me that they have a 75 by 4 matrix locally in their memory, where 0 has the first half and 1 has the second half. I can also perform now a min operation on this data along an axis. Again, I'm choosing the axis 0 here. Minimum would now have to compute across both of the data chunks and along the decomposition boundary. This is transparent to the user and he does not have to explicitly write any communication codes. Instead, HeAT is doing this internally. How this is done is by performing a local minimum operation and then exchanging data via MPI and once again performing a minimum operation on it. As you can see, after the operation, both 0 and 1 have the correct result of the minimum operation. What you can also see is that both now have a copy of the data with split none, because we have performed the reduction operation across the domain decomposition boundary. By now, HeAT implements almost all of the low-level NumPy operations. I can use them now to compose higher-level algorithms for actual data analytics tasks. HeAT provides several of these algorithms already as part of its package. We have benchmarked several of these algorithms in a systematic performance evaluation and compared them against other state-of-the-art frameworks. In particular, we have been looking at NumPy and PyTorch as single-node baselines and Dask as a distributed competitor. We were interested in the scaling behavior of each of them, specifically how they behave under weak and strong scaling conditions. Weak scaling refers to the process of doubling the processing work while doubling the amount of processors that you are using. Optimally, you would be observing an efficiency flatline. Strong scaling instead leaves the amount of work constant while doubling the processors. Optimally, you see a linearly increasing line of speed up of your computations. At first, we have looked at the performance of matrix multiplication for each of the frameworks. For the matrix multiplication experiments, we have multiplied the cityscapes image with a 128 long vector of random numbers as to mimic what would happen in a regression or neural network computation. In blue, you can see HeAT, in red, Dask, in turquoise, PyTorch, and in orange, NumPy. Moreover, in black is a line for the maximum GPU peak performance that we could have achieved. On the left-hand side, you see the weak scaling experiments. On the right-hand side, the strong scaling experiment. Additionally, I should mention for the Dask experiments that we have distinguished between auto and tuned, where auto refers to Dask's automatic partitioning of data. In tuned, we have selected a chunking size for Dask datasets that is equal to what HeAT would do internally. As you can see, HeAT exposes a very strong weak scaling behavior with an almost flat line. We have measured here the throughput, so the number of operations performed per second and process. Dask initially is somewhat faster than HeAT, however quickly decays and exposes a suboptimal weak scaling behavior. Also, HeAT exposes a very similar performance than PyTorch for the GPU backend and NumPy and PyTorch on the CPU backend. For the strong scaling experiments, we have measured how much faster each of the frameworks is compared to NumPy. So NumPy is the baseline value. As you can see, HeAT again exposes an almost linear behavior both on CPU and GPU. Dask has initially a similar behavior and scales well up to 4 nodes, but afterwards decays quickly. Overall, HeAT outperforms Dask by a large margin, up to 3 orders of magnitude if we allow a comparison between CPU and GPU backends. In a second performance evaluation, we have implemented k-means clustering, where we try to identify 8 cluster centers. Once again, we have depicted here HeAT, Dask, PyTorch, and NumPy. On the left-hand side, weak scaling, on the right-hand side, strong scaling. You may note that several Dask data points are missing. These are due to memory exhaustion errors where we were unable to acquire data points. Yet again, to the scaling behavior, HeAT outperforms the other frameworks both in weak and strong scaling, with flatline behavior on the left and linear increasing behavior on the right-hand side for CPU, and at least a flatlining behavior for GPUs. This is mainly motivated due to memory bandwidth limitations of the GPUs. Okay, let's summarize what you guys have heard so far. HeAT is an accelerated and distributed tensor framework in the Python programming language that allows you to tackle numerical big data challenges. It follows the batteries included philosophy, meaning it provides low-level features under the hood that do heavy lifting and high-level algorithms for convenient use. Features that I have not mentioned so far, but HeAT provides, are GPU direct intra-node communication, parallel input and output to disks, including supported CSV, netcdf4, and HDF5 formats. Also, among the high-level analytics algorithms, you will find cohorted networks, lasso regression, and data parallel neural networks. HeAT is already in productive use in several scientific and industrial applications. There it is being used to analyze datasets that are in the order of 100 terabytes in size. Specifically, it is used for airplane design, the analysis of patterns in hydrology simulations, as well as predicting folding processes for proteins with medical applications. Soon, we intend to extend HeAT with additional features. This includes first and foremost so-called automatic differentiation, or AD, over the wire. This will allow us to implement automatized model parallel neural networks. Beyond that, other features are planned which you can monitor on our project web space. Perhaps you want to get involved in collaborating and further developing HeAT. A lot of work went into the development of HeAT. With this slide, I would like to acknowledge all the collaborators, admins, assistants, code contributors, etc. that helped us in developing HeAT. I would also like to acknowledge our funding agencies, specifically the Helmholtz Association and its Initiative and Networking Fund that made this project possible under the project grants for Helmholtz Analytics Framework and Helmholtz AI. If you would like to try out HeAT yourself, that is very much possible. It is an open source software under the liberal MIT license. You can install it directly from the Python package index PyPy using pip install HeAT and start coding. Or it is also possible to clone the latest greatest repository directly from GitHub using the URL provided below. That being said, we hope you feel the heat and it accelerates your big data computations. I am open to questions now.